Welcome everyone to your first technical session at Interview Kickstart. My name is Omkar. I'm the head of curriculum here. Hopefully you've gone through the pre-class videos for sorting and been hearing my voice for over 6 hours, unless you've been speeding it up, which is what some people tend to do. So that's just for your information, because you'll be watching my pre-class videos for all the 5 algorithms topics. So one way you can go through them faster is by just setting your speed to 1.25x or 1.5x. So the agenda for today is, you can expect the class to go up to 4.5 hours. The only thing, so sometimes though what happens is some cohorts want to go farther than that, and I don't know what you think, but my goal is not to cover all the problems that I'll be showing you, but if you want, we could go through more problems than hi. Sorting class? Yeah. So here's the agenda. I'll spend the first 20 to 30 minutes giving you an introduction to problem solving and coding patterns, which will apply for all the 5 algorithms classes. And then we'll look at interview problems related to sorting, which are basically of 4 types. Pre-sorting and extensions of merge sort is what we'll do before the lunch break. So lunch will be provided right outside the classroom for those of you who are here. And after the lunch break, we'll do some problems which extend quicksort and heapsort. So when you're preparing for interviews, there are 2 aspects of your preparation. The first aspect is problem solving, and the second aspect is coding fluency. And let me talk about both over the next 20 minutes. A problem is a question for which you have no idea, at least initially, what method will work. So if I give you, for example, this question where you have to multiply 2 large whole numbers, it might take you a lot of time, you might make calculation errors, but there is no doubt as to what method you have to use to solve the problem, because we've all done grade school arithmetic. A problem is a different type of question. It's not an exercise. This is an exercise. When you're solving a problem, you will feel clueless at the beginning. So what we need to do to solve questions that we have not seen before, for which we have no idea what method to use to solve them, is to spend time investigating that question, deploying general problem solving strategies. And these problem solving strategies depend on the domain from which the problem comes. If the problem comes from math or science, they have their own problem solving strategies. We are concerned here about computational problems. And so we specifically look at strategies for solving computational problems, which are algorithm design strategies, because the solution to a computational problem is an algorithm, a method that solves the problem. And these algorithm design strategies are the ones that you would have gone through in the pre-class video: brute force, decrease and conquer, divide and conquer, and transform and conquer. So the intent of an ideal technical interview is to first see how good you are at problem solving, how good you can handle questions that you have not seen before. And the second part of the interview is, once you and the interviewer agree that you have arrived at a correct method to solve the problem and an efficient method to solve the problem, then you have to implement it as a program. So these are the 2 parts of the interview. So this is going to test your problem solving skills and your coding skills. And both of these might depend on your knowledge of computer science and engineering fundamentals. So all these are the three things that you have to work on when you're preparing for interviews. So the goal of the pre-class videos is to provide you those fundamentals in computer science and engineering. And then in the live class, we focus on the problem solving skills, and the coding skills are what you would be practicing when you are when you're coding up these problems directly on the IK web interface or lead code or wherever um, you're actually implementing the code. Now, the problem is that there is a tension between the time that problem solving requires and the severe time limit that an interview has. So there are broadly two ways to go about dealing with this tension. The first is to try to go through as many problems as possible and memorize their solutions, hoping that you will be lucky enough to be given a question that you've seen before in the interview, so that at least there is no problem solving to be done. You can pretend that you're solving the problem on the spot, whereas in reality you're just retrieving the solution from your memory. And so the task then just reduces to coding it up. So that might work with some people. I've heard of some of my friends I've got through Facebook and other companies, LinkedIn and all, by using this strategy. But you're depending on luck if you do that. And I assume that you've joined IK because you want to be prepared for the worst case. You want to become a problem solver, so that if you're given a question you haven't seen before, you have the inner confidence in yourself that you can tackle it, and you won't have a brain freeze, which is what you'll have if you try to memorize solutions to too many problems. Because the moment you're given a question you have not seen before, you haven't been practicing solving questions by adopting these algorithm design strategies. So you'll most likely have a brain freeze. So that's what we want to focus on in this program. We want to make you a good problem solver so that you develop that inner confidence, which is extremely important when you walk into an interview. At the same time, we will expose you to the popular interview questions so that you should be familiar with what is being asked nowadays. And we're going to try to group these problems based on patterns, coding patterns, and also algorithm design patterns, so that rather than going through one random problem after another, we will go through a cluster of problems together so that they all seem to be fitting together into a coherent pattern. So that way, you don't have to treat each problem independent of every other problem. You're essentially going through one pattern after another. So time tests always cause anxiety. This is true for kids who have math anxiety because of it in school. It's also true for experienced engineers who are giving interviews. They also have interview anxiety. So the best antidote to this anxiety is to become a problem solver, so that, as I said, that inner confidence is what is important. It's a signal that you're ready to give an interview. Because you would have done this repeatedly as part of your prep. If you're given a question you've seen before, well and good. But even if you're not, even if you haven't seen that question before, you know that you have the ability to make progress on it. And that if it's really hard for you, it's going to be hard for a lot of other people as well. Now, the first time you're given a question that you haven't seen before, or the first time you see a problem, try to spend time on it. Don't look up the solutions. Some people have the habit of looking up the solutions in 5 or 10 minutes. They don't make progress. Avoid that temptation, because you want to build your problem solving muscles. And once you have solved that problem, then you will have to come back to it multiple times, not for the problem solving part, but for the coding fluency part. But at the same time, you should not forget your very first journey to solve the problem, because if you're asked that question in an interview, you should be able to retrace that journey to show that you're a problem solver and not just retrieving the solution from memory. But the next time you come back to that same question, it is no longer a problem for you, it's an exercise. So you should focus on coding it up fast. And that's where these coding patterns come in. You want to practice these patterns over and over so that they just become part of your mind. And when you're writing the code, you're not writing the code from scratch. You already have the pattern in your mind. You write it down and then you focus only on changing it, editing it. So if you're given this question um, of sorting an array of integers, hopefully this is not a problem for you anymore. It's an exercise. Maybe it was already an exercise before you went through the pre-class videos. Which algorithm would you use to solve this problem or question? Yeah.
So doesn't it depend on the constraints?
Yeah. So for many of these problems, there may not be a single well-defined answer. It's going to depend on what you're given. So if you're given an array of integers, what are the different options that you have in mind? Radix sort could be something that you use specifically for integers.
Use sort from
Yeah, so for this particular question, the intent of giving this question is to actually implement some sorting algorithm rather than calling the sort function. There will be other problems where calling the sort function will be okay, and that's something we'll go through. Somebody had a suggestion online?
I said insertion sort in case of best case, like if the array size is small or if it is already sorted kind of thing.
Yeah, so if you're given that the array is almost sorted, only a few elements are out of order, then insertion sort does well, because every iteration of insertion sort will insert one of those elements that are out of place. You just have to do the work for inserting an element which is out of place and not worry about the other elements which are already in place. So insertion sort will basically skip over those. So if the array is very small or if the array is almost sorted, insertion sort works well. If you will only be sorting in integers, radix sort might work best. If it's a general sorting algorithm, I mean, if you have to sort, let's say, arbitrary objects, what would you use?
Merge sort?
Quicksort?
No.
Okay, again, it depends.
I think if you have multiple keys, yeah, it depends.
So when would you prefer merge sort? When would you prefer quicksort?
If stability is important, we'll go for merge sorts.
Yeah, if stability is important, you would go for merge sort. If you're not allowed to use auxiliary space, then you would use quicksort or heap sort, given that merge sort does require auxiliary space. So between quicksort and heap sort and merge sort, in terms of running times, you might remember from the pre-class videos that empirically quicksort tends to run faster in general, even though it's theoretically possible for it to run in quadratic time. That's the worst case time, but it very rarely happens. So this is not a university course. So in an interview setting, you would pretty much assume that quicksort is going to run in n log n time. Right? We don't distinguish between worst case and average case, given that the worst case almost never happens if you're using the randomized version of quicksort, if you're picking a pivot randomly. So there are two scenarios where the average case can pretty much be assumed as the worst case in an interview setting. Don't call it the worst case though. The first is quicksort and extensions of quicksort, and the second is operations on a hash table. Operations on a hash table can be assumed to run in constant time in an interview, even though theoretically we know that they might take linear time. Are you all familiar with the basics of hash tables?
Yes.
So you'll learn a little bit about them in week 3, but hopefully at least you know how to use a dictionary, whatever programming language you've used. So now how fast, so we've gone through the different trade-offs. If you want stability, you use merge sort. If you want fast execution time, you use quicksort. If you want an in-place algorithm which doesn't use auxiliary space. You use quicksort or heapsort. So again, there's no one single answer to this, and you should be able to discuss these trade-offs. Now, you should know how to code up merge sort, quicksort, and heap sort in whatever language you've chosen. The target should be to be able to code up merge sort and quicksort in less than 10 minutes. Okay, so don't worry about the code that I have here. I usually have Python code on my slides. That's just for reference. I don't assume you're coding in Python, but just to show you that whatever we are discussing here has been tested. So how many of you have not been coding for a while? Yeah, so if you try to code up these algorithms, you might take a lot of time initially, but as you keep practicing over a month or two, you'll find that you'll get fluent at coding. It's like learning to drive a car. Initially, you have to pay attention to all the small details, but then it just becomes something you learn to do unconsciously. So the reason why I'm saying you should learn to code merge sort and quicksort in less than 10 minutes is because both of these algorithms, the code for them, can serve as templates to solve related problems. So pieces of merge sort, pieces of quicksort, as you'll see, will be used to code up the solutions to other interview problems. Heap sort is something you should be able to do in less than 5 minutes because you won't be implementing a heap from scratch. You would be just invoking a library function for building a heap on the array and then extracting the elements one by one and dumping them into some result.
And I have a question, like in case if we use JavaScript, I don't think we have these kind of things that we can import. So in that case, do we need to implement from scratch?
In an interview, it's very unlikely that they will ask you to implement from scratch because that would be a separate question. So the
Okay.
question that you would be given would be one where you have to use a heap.
Mm-hmm.
And if they ask you to implement one, then to be fair, they should give you extra time for that. But yes, you should know how to implement a heap. I did go through that in the pre-class videos.
Yeah.
Regardless of what language you use, you should be able to implement a heap. What you can do for your prep is implement it once and then just copy and paste the code for all the problems that you do as part of your prep here.
Mm-hmm. Makes sense.
Now, coming back to this problem solving part of prep, there is a change that is required in both our mindset, our mental discipline, as well as our emotional outlook towards these questions. The change in mental discipline is that we need to get habituated to doing open-ended experimentation and failing. As I said, if you're not used to working for more than 5 or 10 minutes on a single problem, you should increase that time scale of concentration. You should learn to work on a problem for an hour and a half. It's very unlikely that you'll make no progress at all if you're deploying the different problem solving strategies that you've seen in the pre-class videos and we'll discuss today. So if you still don't make progress in an hour and a half, you can take a break and then come back to that problem later, maybe sleep over it or come back later in the day. So the time scale of concentration required needs to increase because that is how you will learn to build those problem solving muscles, which are going to be important as far as developing inner confidence is concerned. And failure is something that we need to embrace as part of problem solving. We need to have this attitude that investigation is always worthwhile, even if it leads to a dead end. Many times we might be able to extract general lessons from failures on individual problems, which can help us avoid making those same so-called mistakes on other problems. The second change is a change in our emotional attitude. Most people tend to think negatively about questions for which they have no idea what method to use. And so if you haven't done problem solving ever as part of your education, school or college education, it really requires a change in emotional attitude. most people are used to working on exercises, lots of worksheets, including children. That is analogous to working out at a gym. The motions are very repetitive. You need music or something to keep yourself entertained while you're going through those repetitive motions. They do help you to build your muscles, but they don't help you to learn to do new things, to solve new problems. So problem solving is more like mountaineering rather than exercising at a gym. When you're hiking in a national park, you want to scale a peak. That is analogous to problem solving. You have no idea what path to use. Maybe you don't have a trail map. You see 5 different trails going in different directions. You have no idea which of them will lead to the top of the peak. So you have no option. You just pick one of them and then just go in that direction, and then you might find that it leads to a dead end, in which case you backtrack. You try another trail. And so you keep doing that. It might take a lot of time. You might get dirty. You might get rained down upon. But at the end, when you reach your destination, there is a lot more satisfaction. You feel that you have discovered the solution yourself. And the journey itself is something that is enjoyable when you are hiking. Right? Exercising at a gym isn't necessarily enjoyable unless you have music or something to listen to. So if you don't feel lost while working on these questions, it means you're not really problem solving. So it's not just okay, but it's expected that you will feel clueless and lost at the beginning, and that you will need a lot of time. Now, problem solving is an art, but it's also a craft that can be learned. And part of learning to be a good problem solver is to build domain knowledge. As I said, those computer science and engineering fundamentals, which will provide you through the pre-class videos. You should also learn how other people solve problems. So learning from an instructor is part of the program, but it's equally important to learn from each other and to use the Slack channel that you have to share solutions and to ask each other questions, as well as your difficulties and your frustrations. Cohorts which use the Slack channel very actively tend to have a superior learning experience. And that will continue well into the support period. If you're really active on Slack, you will actually get a lot more out of the program, because you'll see that many other peers have the same difficulties, the same questions. And so as you help each other, you might find that different people have different ways of thinking about the same question, which is very useful to know. Especially learning from each other's failures. You don't have to fail yourself in everything. You can learn from other people's failures as well. Problem solving is also an active process, which means you can't just do it by passively absorbing it from an instructor. It's like hiking. You can't learn hiking by watching a video or listening to a lecture on hiking. It's something you have to do. You have to engage in yourself. So with that, let's begin looking at some of the interview problems on sorting, related to sorting. For the purpose of this live class, I'm going to assume that these are the main points that you've taken away from the pre-class videos. There are other details in the pre-class videos which may not be relevant for today's class. So this is just what I'm expecting you have taken away. General algorithm design strategies that I've talked about, basically these 4 general strategies, and we'll see how they keep getting used today. You should have learned the basics of algorithm analysis, the fact that you need to develop a correct algorithm and how to measure the efficiency of that algorithm, time and space efficiency using the big O notation, as well as learning to focus on the worst case times. Improving the worst case complexity is what is most crucial. Optimizations which work better on specific inputs, but which don't improve the worst case complexity, are not as important or relevant as optimizations that improve the worst case asymptotic complexity of algorithms. So you should have learned the difference between worst case, average, and best case. And the sorting problem was used as a case study to teach these general algorithm design strategies and the basics of algorithm analysis. Okay, and the three main sorting algorithms that you should have taken away are merge sort, quick sort, and heap sort. These are the ones that you should know how to code fast and which we'll be using today. By the way, I hear some background typing noise from somebody online. If you're not speaking, please mute yourself so that um, we don't hear sound from you here in the live class. Okay, so let's begin with, so as I said, there are 4 categories of problems that we're going to cover. And before I give them a name, let's actually go through one of the questions, one of the problems in each category. And then once we solve this problem, we'll give it a name. We'll give the category a name. So how many of you have seen the two-sum problem? Okay, more than half of you. So this is by far the most popular interview question. If you look at lead code statistics, you see that this is number 1 in terms of popularity. Also, it's the very first problem that was added to lead code, so it has an ID of 1. So my goal here is not to tell you the solution to this problem. My goal is to try to show you how you would come up with the solution. And if I just tell you what the solution is, that's something you can get from from YouTube or other sites. What we are interested in is learning how can we come up with the solution if we had not seen this question before. So this question is found in Data Structures Algorithms books. If you're familiar with Corman or Steven Skena's Algorithms Design Manual, the two-sum is found in both of them. And so that's probably the source of all the variations of this problem that you find on LeetCode and other sites. So the basic version that you find in the algorithms textbooks is the following. You have an array of n numbers and you have another number given, which is a target. Now these numbers could be integers, they could be real numbers, doesn't matter. You want to find out whether this array contains 2 elements whose sum equals the target that you're given. For example, if the array that's given to you is this 5913 and the target value is 6, are there 2 numbers here which add up to 6? Yes, 5 and 1 add up to 6. So you have to return yes as the answer. But if the target value was changed to 7, then you can see that there is no pair of numbers here which adds up to 7. And so in that case, you have to return a no. So it's a question for which the answer is a yes or a no. These types of problems are called decision problems. It's a general word for problems where the output is either a true or a false, a yes or a no. And later on, you'll see that the same problem can have a decision version, right, where you have to output a yes or a no. It can have a counting version where you have to output the count of something. It can have an optimization version where you have to optimize, find the minimum or maximum of something. And particularly when you move to topics like dynamic programming, you'll see that the same context, but the problem could be a decision problem, could be a counting problem, could be an optimization problem. So the two-sum problem is a decision problem. So how do we go about solving this? What would be a brute force way? So let's go through the 4 algorithm design strategies you've learned about in sorting. What would be a brute force way to solve this problem?
Nested loop.
Yeah, so a brute force way is something that follows from the statement of the problem. So if the problem says that you have to find out whether the array contains 2 elements, a pair of elements whose sum equals the target, well, the brute force way would be go through all pairs of elements and see if any of them add up to the target. Right, so you'll have a nested for loop, double for loop, which will, for I varying from 0 to n minus 1, for j varying from I plus 1 to n minus 1, something like that. You check whether array of I plus array of j is equal to the target. If so, you return a true. Otherwise, it's at the very end that you would return a false if you didn't find any pair of elements adding up to the target, you have to wait till the very end before you return a false. So that's the brute force way. What would a decrease and conquer strategy look like? Yeah.
You sort the array in ascending order, and then you have 2 pointers, and then you check to see if it's above the target or below the target, and then move based
Okay.
on that.
So we'll come to that. That is actually a transform and conquer strategy.
Yeah.
So in the pre-class videos, you would have learned about transform and conquer in the context of the sorting problem, where you're given an unsorted array. To sort it, one way is to take that input and represent it in a different format. Represent it in the form of a complete binary tree. So that's one popular way to sort an unstructured input, an unsorted input, represent it as a complete binary tree, and that allows you to perform the operations on that data in log n time. Right? That was the motivation for heap sort. So that's one way to transform the data. We'll look at 2 other ways to transform the data. But what you're referring to, sorry, what's your name?
Chris.
Chris. What Chris referred to is another way to transform the data, which is to sort it. So when you sort your data, that can allow you to do pre-processing, further processing on it to solve the problem later on. So I couldn't talk about sorting as a way of pre-processing because the problem itself was to sort in the pre-class videos. But now I'm telling you that sorting is, this class of problems that we are looking at, I call them as pre-sorting problems because what you do first is to sort the data, transform the data in sorted order, and then you can do further processing. But let's come to that at the a little later. What would a decrease and conquer strategy look like?
Your second array should be a, you need not start it all the way back from top, but you use it with an offset.
Okay, so let me actually, okay, I need to tell operations to switch to the notepad just a second. Hi, Steph, the notepad is not there. Yeah. Yeah. So I hadn't. So it wasn't there from the beginning. Yeah. Is it spotlighted? Okay. So people can see this online, right? The notepad.
Not yet, no.
No.
It shows up as like a person. Oh, there it is.
Okay.
Yes, we can see now.
Okay, good. So in a decrease and conquer strategy, what you do is you're given a problem of size n and you think of chipping it off a little, either from the right side or from the left side. Well, one way of decreasing is by chipping it off a little bit from either end. So what if I could decrease the problem size to n minus 1 from n? And I don't worry about how I'm going to solve the problem on on this. I'm not going to worry about how I solve this remaining problem. I will assume that I hand over that task to someone else. And if that other person has come back with the solution to it, then either before they come back with the solution or after they come back with the solution, I learn to, the only work I do is incorporating this single element into that overall problem. So we need to find a pair of elements which adds up to the target sum. So I will decide to focus only on this piece. Is there a pair of elements involving this particular element? So I need to find if this element has a counterpart with which it adds up to the target. If there is, then I'm going to return a true. If there is not, I just stop thinking. I just say, well, I'm going to focus on a smaller problem size of n minus 1. So this is something that naturally leads to a recursive algorithm. So next week you'll learn about recursion more explicitly, but a decrease and conquer strategy is something that naturally leads to recursion. You can code this up recursively. You can say, I'm going to focus on the first element, see if there is a pair involving it. If not, call the same function recursively on a slightly smaller problem size. Now, this is something you would have learned in the context of sorting. What sorting algorithm is this associated with, this strategy?
Insertion sort?
Insertion sort. You can, again, depends on how you think about it. You can also associate this with selection sort. You can say, I'm going to focus only on determining what this element should be. If the problem was to sort a bunch of n numbers, I'm going to say, let me focus only on generating this number. And this should be the smallest number. So I find the smallest number and I put it here. And then I delegate the task of sorting the remaining array to somebody else. So that leads to selection sort. If I decide that, well, I want somebody else to sort the first n minus 1 numbers or the last n minus 1 numbers, and then I'm going to incorporate this isolated number into that sorted output, that leads to insertion sort. Right, so both selection sort and insertion sort can be thought of as decrease and conquer. I mentioned selection sort as a brute force algorithm, but again, it depends on with using what strategy did you arrive at that algorithm. That's how we give names to these different algorithms. You know, that's how we give strategy names. Now, this decrease and conquer method would definitely work for two sum. What would be the complexity? So if I had to write the time complexity on a problem of size n,
Quadratic.
yeah, so clearly I'm depending on someone else to solve the problem on a slightly smaller problem size. What is the work that I myself did? The work that I myself did was to test whether this first element is part of a pair that adds up to the target. And for that, I had to search for its counterpart by doing a linear scan in this array. So that's going to take time proportional to n minus 1. Right, let me just write it as c times n minus 1. And so I can open this up. This is actually similar to the recurrence that we got for insertion sort. If I open this up, I'm going to get, right, t of n minus 1 can be written like that. And so eventually you can see this is going to end up taking quadratic time. Right, as I keep opening up, I'm going to get a series. C times n minus 1 plus c times n minus 2 plus c times n minus 3. You may not even need to do this math. You could just see intuitively, right? If you just see what steps we are doing, this number is going to be paired up with n minus 1 numbers. Then the second number is going to be paired up with n minus 2 numbers. The third number is going to be paired up with n minus 3 numbers. So that's going to take quadratic time. Is this an improvement over the brute force approach? No. So we don't have to proceed further. We stop. Let's try divide and conquer. In divide and conquer, you're given a problem of size n, and you split it up, not from one end, but from the middle. Assume that you have two subordinates. Think of yourself as a lazy manager. You study that next week when you look at recursion in more detail. One way to grapple with recursion is to use an analogy which I call the lazy manager's analogy. You imagine yourself as a lazy manager who's been assigned this problem. you don't want to do, you want to minimize the work you do. So you want to rely on your subordinates to actually do the work. And so in the decrease and conquer strategy, you have one person who you delegate this work to, and what you do is just this part. In divide and conquer, you split up the problem into two parts, and you have two subordinates under you. You assign the left half to one subordinate, you assign the right half to one subordinate. You assume that they both come back with the right solution for these two halves. And now you focus only on merging their work, combining their work, and solving the problem you're given, and then passing it back up to your boss. So if these two people, if either of these two people came back and said that they found a pair within the left half or within the right half, which added up to the target sum, what would you conclude?
Yes.
Then the answer is a yes. If they found a matching pair, then I can declare that there is a matching pair in the whole array. What if neither of them found a matching pair that adds up to the target?
Try to.
Yeah, then it's possible that there could be a matching pair where one of the elements lies in the left half and another element lies in the right half. So you have to do the work of trying out all possible such pairs. Right? There are n by 2 pairs on the left. Sorry, n by 2 numbers on the left, n by 2 numbers on the right. How many pairs do you have to test? For each of these elements, you have to test whether these other n by 2 elements adds up to the target, right, when combined with that element. So if I were to write this down, I'm going to write this as the total work that was done in the corporate hierarchy was the work done by the two subordinates, right, which was T of n by 2, and the work that I did as the lazy manager, which was trying out all pairs. How many such pairs are there? Yeah, n by 2 times n by 2. So something that's proportional to n by 2 times n by 2, right? C times n by 2. So this is something that is order n square, right? This work is something that's order n square. Now, I don't even need to solve for T of n because I already see that I'm doing quadratic work in this. So I can stop and backtrack from there, because I couldn't improve the brute force solution, so there's no point in continuing further. So that's the divide and conquer approach. Now, the transform and conquer approach would be to change the representation of the data. And one of the suggestions here was to sort the input array. That's one way. The other way that you've already seen in the pre-class videos is to represent the array as a balanced tree of some kind. Right? You saw heaps in the pre-class videos. There are other types of balanced trees. A third popular way of transforming the data is to represent the data in a hash table. I mean, dump the data into a hash table. So let's look at the sorting based solution first. So you're given an input array and Chris suggested you sort it. So assume that your numbers are now sorted. How much time would this have taken? Order n log n, assuming you used an efficient sorting algorithm, one of the three. And then once your numbers are sorted, how would you search for a pair of numbers which adds up to the target?
Can we do iteratively find one node and find its pair by subtracting that value from the total target?
Right. Yeah, if you, for any number, you know what the complementary number should be. So basically you could search for that complementary number. That's what we were doing even in the decrease and conquer strategy. You start from the leftmost, you focus on the leftmost number and you search for counterpart number. But you were forced to do a linear search there because the array was not sorted. Here, I could now decide to do a decrease and conquer approach where I focus on this number and I say, well, can I search for the counterpart number here? But now the array is sorted, so what would I do to search? Binary search. I could focus on this and I say I'm going to do a binary search and my binary search, let's say, finds a counterpart. That would have taken time at most order log n. But let's say I couldn't find a counterpart number. My binary search terminated somewhere here. Right? All these numbers were less than the counterpart number I was searching for. All these numbers were more than the counterpart number I was searching for. So now I look at the second element and I see, does it have a counterpart? So again, I do a binary search on the remaining array. And so how much time would that take?
N log n.
N log n.
N log n, because log n time for each number would be a total of n log n time. So in addition to this order n log n for sorting, I would need order n log n more time to follow this binary search based approach. The total time using this approach would still be order n log n. Now, one thing you might have noticed here is the first binary search, let's say the first binary search terminated here. When I'm searching for the counterpart number for this, do I really have to look at the whole array? No, because if my first binary search terminated here, all these numbers were more than the counterpart, all these numbers were less than the counterpart for this. So when I move on to the next higher number, the counterpart for it will obviously be lower, smaller than the counterpart for this. So I just have to focus my binary search in this range. You can forget about these numbers. You're hearing some noise online, so if you're not actively speaking up at the moment, please mute yourself. Just another reminder. So our binary search can start from where we left off earlier. Likewise, when we look at the third element, our range will be even more constrained. So in some sense, we are we are doing binary search on a smaller and smaller and smaller range, and that how much time do you think that should take in the worst case? What are we aiming for with that kind of an approach? Well, we have to look at all of them. We might have to look at all the elements. There may not be there's no way to avoid looking at all the elements, right? So order n can be thought of as we can't do better than order n. We want to do better than n log n. So given that our binary search is going to move progressively left, at least the right endpoint of it, and our left endpoint is moving one step to the right each time, this leads us to that two-pointer approach which Chris was pointing to, where we could, let's say that we have one pointer focused on this element on the left, and the second pointer is going to, we were thinking of the second pointer doing a binary search, but let's have the second pointer just do a simple scan from right to left until it reaches the place where the counterpart element should have existed for it. If we didn't find it there, we move this forward, and we keep moving left for the second pointer, and so that leads us to that two-pointer strategy. So what's the two-pointer strategy? Let's flesh out the details. So this is our array. It's now sorted, and let's say these are two numbers which add up to the target. How are we going to find them? So we have two pointers, I and j, which start out like that. So how do we check whether we have found the right pair of numbers? Well, we add these two numbers. If they add up to the target, we are done, we return a true. What if they don't add up to the target?
If they are larger,
They're less.
So if they are less than the target, that means this number right? In the process of moving right, we reached a number which is actually less than the target. So there is actually no counterpart for this number on the left. So we have to increment the I pointer in that case to the next element. What if the two numbers add up to something more than the target? Then it's like we are still doing that binary search kind of thing. So we just keep looking further to our left. We decrement the J pointer. And the claim is that at some point, both I and J are going to come here. Why is that guaranteed? Because let's say that the I pointer reached here first. Right? We know that in each step, either I is moving to the right or J is moving to the left. So one of them is going to reach a red number. We don't know which one. Let's say it's I. And let's say at that point, J was somewhere here. What would this number and this number add to? Something that's equal to the target, less than the target, or more than the target?
Higher than the target?
Higher than the target, because these two numbers add up to the target, right? We are assuming this solution exists. So this plus this should be more than the target. And what do we do when we decided that when they add up to something more than the target, we decrement the J pointer, we move it to the left. So we'll keep moving it to the left until the J pointer reaches here. And that at that point, we will discover this pair of numbers which adds up to the target, right? If on the other hand, the J pointer had reached here first and the I pointer was somewhere over here, what would these two numbers have added to? Something less than the target, because these two numbers add up to the target. So this number is smaller than this number. So the sum of this and this would be less than the target. And in that case, we decided to increment the I pointer. And so we will keep incrementing the I pointer because all of these numbers will add up to something less than the target when added up with this number. So we'll keep incrementing the I pointer until the I pointer reaches here. And at that point, we will discover this pair. So our algorithm is guaranteed to be correct. And it's going to terminate in how much worst case time? Yeah, so this 2-pointer pass is going to be linear.
Is it order of n?
Yeah, linear means it's going to be order of n. Because in each step, we are either incrementing the I pointer or decreasing the J pointer, right? Depending on the outcome of that comparison. If the sum of those two numbers is equal to the target, of course, then we are done. If it's less than the target, we increment the I pointer, else we decrement the J pointer. So what's the total time?
N log n plus order of n.
The total time based on this pre-sorting approach would still be order n log n, because that's governed by the time it took to sort. So let's look at this.
Quick question. We are assuming that the pre-sorting function will just use the best one to get to n log n.
Yes. So in pre-sorting problems, you don't have to worry about the internal details of what sorting algorithm you're using, right? You just call nums.sort or whatever the array that you're given is. You assume that it's going to be either merge sort, quicksort, or heap sort. And if there is a constraint that you're not allowed to use auxiliary space, then you won't be using merge sort. But you just say nums.sort and that should be enough. You can say that sorting can be done in place if we use quicksort or heap sort. And so we don't worry about implementing them, right? Now, what if we represented the same numbers in a balanced tree? What is a balanced tree? When do we say that a tree is balanced?
Like a black tree.
Yeah, it's some kind of tree. Even a heap was a balanced tree. It's a tree whose shape looks like this, right? All the levels are either completely filled or almost filled or mostly filled in a way that the height of the tree is going to be log of the number of elements in the tree, right? And balanced trees are always good because when the height is bounded by log n or something proportional to log n, the height is order of log n, then then a search operation on this tree is going to follow a path from the root down to some node. And so following any path is going to bound the search by the length of the path, right? Maximum possible length of the path, which is going to be log n. So which is why it might make sense to represent the array as a balanced tree. Now, in the case of a heap, we could have built the whole heap in order n time. Here we are not using a heap, right? Why? How would we use a balanced tree to solve this problem? Let's say all the numbers were organized into some kind of a tree.
You want it to be a binary search tree, so when you were looking at a node, you could say,
Are you all
I need to
familiar
go
with binary search trees? You'll be studying about them in week 3, but I don't want to emphasize this method much, but there is actually a variation of twosome in which the numbers are given to you in the form of a binary search tree, and you have to find if there is a pair of numbers which adds up to the target sum. So in a binary search tree, there is a way to traverse the tree so that the elements are sorted. Okay, that's called an in-order traversal. You'll learn about that in week 3. But I just want to leave it here, saying that you could follow a two-pointer strategy on a balanced binary search tree. You start from the smallest number on this I pointer will start from the smallest number inside this tree. This j pointer will start from the smallest number inside this tree, and they will walk towards each other, very similar to how they were walking in an array, except that they're walking up and down. They're iterating over the elements in order traversal. So how much time does it take to build this binary search tree on the given input? You may or
Order
may
of
not know. Yeah, so just like in heap, so if you can do insertion into a tree to keep it balanced in log n time, you can actually build this whole balanced binary search tree in n log n time, which is equivalent to sorting, right? So n log n time to build the tree, order n time to do the two-pointer pass in the tree, and that would again be order n log n. But this, of course, there's no advantage of using this over this, which is why I don't want to emphasize this, because this is simpler. But I'm just pointing out that there could be other problems where, and there are variations of twosome you'll see on LeetCode where the input is given in the form of a binary search tree. Let's look at this.
Quick question: why is the construction of the balance tree n log n?
So
Should
you will
be
learn
ordered
about, you will see how insertion is done in a binary search tree in week 3. But assuming that insertion can be done in log n time, how much time would it take for you to insert all the elements one by one? Right, inserting the first element is constant time. Inserting the second element would be log of 2.